Hello and welcome to this next video about quantitative chemistry, so that's all the calculations part of chemistry. And in this video we will be considering how we calculate the relative formula mass of a particular substance, that's the MR, how we calculate the percentage by mass of different substances. We'll explore the concept of the mole, not the animal, and we'll look at Avogadro's constant. So first up, we'll need to look at relative masses. Now, atoms are absolutely tiny, far too small for us to measure easily what the mass of one atom might be. So if a scientist wants to work with the masses of atoms, it's far easier for them to... Now, the first thing that we need to do is consider relative masses. Now, atoms are absolutely tiny. They're far too small for us to easily measure what the mass of one atom might be. So if a scientist is going to work with masses and atoms, it's much easier for them to compare the mass of one atom to another. So if we have a look at the atoms that I've got here, I've got three different atoms that I'm just representing as circles, and so we can't really measure what those atoms' mass might be. But what we can do is we can compare the mass of one atom to another. So if we look at these atoms that are on here and we decide that this one on the right hand side is going to be magnesium, and then we say that this one in the middle is going to be carbon, and then that one on the left hand side is going to be hydrogen. What we can see from the periodic table's numbers is that we've got these different numbers for each element and along with their symbol, and this number at the top we have called this mass number in earlier topics when we've been looking at atomic structure, and this one here is the proton number, which we're not actually going to use today. What we can see from these numbers then is that the mass of hydrogen, this mass number, is 1 and the mass of carbon is 12. So what that means is that carbon is 12 times heavier than hydrogen. So if we had one atom of carbon over here, what we would need to have to balance it on this seesaw is we would need to have a total of 12 hydrogen atoms on the other side. So we don't actually know what the masses of these atoms is or are, but we can see that we've got 12 hydrogens here and 1 carbon over here. So the mass of hydrogen is 1 compared to carbon, which is 12. And then if we move over to compare magnesium to carbon, this time what we can see is that magnesium has got the greater relative atomic mass. So if we had a seesaw here with carbon at one side and magnesium on the other, well then this time the right hand side is heavier, so we need a second carbon on the left hand side to get this to be balanced. So we've got one carbon with a mass of 12 and another carbon with a mass of 12 to balance the magnesium with a mass of 24. So we're comparing the masses of one atom to another. Now I've deliberately used carbon in both of my examples on the seesaw because carbon 12 is actually the reference that everything else is compared to. And the reason that we use that is that carbon's got a really low percentage of isotopes, well, different isotopes. So the mass for carbon can be considered to be really, really close to a whole number, really, really close to 12. Whereas some other elements, in fact, all the other elements, have got a variety of isotopes, which means the mass might not always be a whole number. So because we've been looking at atoms on here, what we've been looking at is in fact the relative atomic mass, which is given the symbol AR, and that comes from, quite obviously really, A for atom and R for it being relative mass, as opposed to what the actual mass of an atom might be. We're going to move on now to look at relative formula mass, which is given the symbol MR over here. Now at first glance that might seem a little bit weird that we're using MR for relative formula mass, but it's sometimes called relative molecular mass, which you can see where the M would come from in that instance. But actually, calling it relative molecular mass is not always accurate because not everything is actually a molecule. So the phrase relative molecular mass would be okay for these because these are covalent molecules. But what we have on the right-hand side aren't molecules. These two are ionic, and so the word molecule would be completely inappropriate to use for those two substances on the right-hand side. And so we use the term relative formula mass because relative formula mass will cover all of these four things in my example, and all of the things that aren't atoms can be considered to have a formula. But like I say, not all of them are molecules. If we look now at what relative formula mass actually is and how we calculate it, so the MR, the relative formula mass, is the sum of the relative atomic masses for all of the atoms in a particular formula. So it's the sum of the relative atomic masses for all of the atoms in a formula. What does that mean? Well, we've got some formula here, and if we have a look at these formulae, we've got water, and if you remember what these formulae mean, we've got 2, that little 2 just belongs to the hydrogen, so we've got 2 atoms of hydrogen, and we've got 1 atom of oxygen. If we look over on the right-hand side here, we can see that this is the relative atomic mass of hydrogen, 1, and there's 2 of them. And over also on the right-hand side, we've got the relative atomic mass of oxygen, the big number for all of these, and the relative atomic mass of oxygen is 16. So to work out what the MR is, to calculate that, all you need to do is add up all of the atoms and all of their masses. And so we've got 18 for water. Looking over on the right, carbon has got a mass of 12, and we've got oxygen again, which is 16, but again we've got that 2 belongs to the oxygen, so 12 plus 16 is going to give us 44 on there. Moving on to methane, we've got 12 for the carbon, we've got 1 for each of the 4 hydrogen, and that gives us a total of 16. And we've got this time, we've got 14 for the nitrogen, that's the AR of nitrogen, and we've got 3 hydrogens this time. So when we add all 4 of those numbers together, this gives us 17. Moving on to 2 examples that are a little bit more complicated, but they work in exactly the same way. These are a little bit more complicated because they have got these brackets that we've considered before. And what you have to remember when you're working with these formulae with brackets is that that 2 means that we've got 2 of everything inside these brackets. And so we've only got 1 magnesium, but we've actually got 2 of the oxygen, and we've got 2 of the hydrogen. So when we're working out the relative formula masses, we need to add together each of these. So the AR of magnesium is 24, oxygen is 16, but there are 2 of them, hydrogen is 1, but there are 2 of them. And we add all of those numbers together, and we get 58. In the same way, on the right-hand side over here, we've got ammonium sulfate, and just like before, we've got a 2 outside the brackets, which means we've got 2 of everything inside the brackets. So we've not got 1 nitrogen with a relative atomic mass of 14, we've got 2. So it's 14 and 14 for the 2 nitrogen. We've not got 1 hydrogen or 4 hydrogen, we've actually got 2 lots of 4 hydrogen, which gives us 8 on there, because that 2 multiplies the hydrogen by 2, and we already had 4 inside the brackets, so 4 times 2 is 8. Then we need to look at sulfur, which has got a relative atomic mass of 32, and there's only 1 of them, because this 4 just belongs to the oxygen, so we've got 4 oxygens on here. So 16 for 1 oxygen, but there is 4 of them, so we need to add all of those together. And when you add all of those together, you get 132 as being the relative formula mass of ammonium sulfate. Now, as well as working out MRs, it's often really useful to work out the percentage by mass of one substance present in a particular compound, in a particular formula. And the way to do that is to imagine the relative formula mass as representing everything in that substance, and then all the atoms of each element that are in the rest of that compound, they make up that whole. So there's atom 1, atom 2 and atom 3, and there's not always the same amount of each atom in a particular compound. And remember, this is percentage by mass, not just how many atoms there are of a particular type. So you calculate percentage by mass by, first of all, working out how much mass the whole thing has, and that's the MR. And then that goes on the bottom here, because what we're going to work out is we're going to work it out as a fraction. And so you need the mass of a particular element divided by the total mass of the substance, and then because it's a percentage, we need to multiply it by 100 at the end. So this is an equation that is really important for you to be able to use. So let's put that into an example, because it's quite hard to get your head around it without an example. And so let's look at this question. We've got, what is the percentage by mass of carbon in this substance here, this formula here? That's calcium carbonate over there, but that's not important for the maths really. So what we need to do first of all is we need to work out how much the whole substance is, because that's the whole substance. And in that we're going to have carbon, we're also going to have some oxygen, and then we're going to have some calcium as well. And so carbon is just going to be a small fraction of that. And so when we look at the periodic table, we find out that calcium's got an atomic number of 40, carbon's got an atomic number of 12, and oxygen is 16, but there are 3 of them, and so we need to include it 3 times like that. When we add all of those numbers together, we get 100. So the total mass of calcium carbonate, that is the MR, the relative formula mass, is 100. And so the percentage of carbon is the mass of carbon divided by the total mass of everything times by 100. And so here the total mass of carbon is 12, the mass of everything is 100, and to turn it into a percentage we need to multiply it by 100, and that gives us a nice easy calculation that we can do in our heads of 12%. Slightly more difficult is, what is the percentage by mass of hydrogen that we find in methane? And this is the formula on here. And so the percentage of hydrogen is the mass of hydrogen divided by the MR of methane times by 100. And so carbon has got an atomic mass of 12, hydrogen has got a relative atomic mass of 1, but there are 4 of them. And so this calculation now is 4, and that's for the 4 atoms of hydrogen, because we did 1 add 1 add 1 add 1. And then we need to divide that by the total MR of methane, which is 16, and then multiply that by 100 to get us our percentage, and this is going to come out at 25% when we put the numbers into our calculator. So the all-important part of this is spotting that there are 4 atoms of hydrogen, and so when we put the numbers into here for the mass of hydrogen, we need to recognise, we need to spot that it's not going to be 1 that goes into this equation, it's going to be 4 times by 1. Then we add all those numbers. What I'd like you to do now is have a go at these 3 calculations. Pause the video, whatever it is that you want to do, or just find the answers later, and have a go at these and then check your answers in just a moment. Hopefully now you've had a go at calculating these 3 different percentages, and so I'll give you the answers now. So for the first one, the percentage of carbon in carbon dioxide was 27.3%. It was actually 27.27%, but I've rounded it up to 3 significant figures because 3 significant figures is the standard number, but watch out, the exam question will probably tell you how many significant figures you need to use. The second one is 17.6% hydrogen. You might have got an answer that was too small, and that, if you did, you're most likely to have missed out the fact that there are 3 hydrogen instead of 1. And then for the final one, that was tricky because you used brackets. You needed to spot that there were 2 oxygen, and so that 2 oxygen is why we've got 32 on the top of this calculation on here, and it's also why the MR of magnesium hydroxide is 58 as opposed to 41 that you might have got if you miscalculated that. So why do we care about percentage masses? In what way is it useful to us? Well, there's a few different uses. First up is in medicines. That's really important to make sure somebody gets the correct dose of drug that they need to make them healthy. Another reason why we might need to know about percentages is for industrial processes, if we were trying to get a raw material to use for a particular substance. And again, we'd need to know how much of one thing that we would need to use in order to get our desired amount of a particular product. So with that in mind, we've got a problem here. What mass of iron would you find in 200 grams of iron oxide? Iron oxide is the raw material that we get all of our iron from, and we use iron for so many different things, so it's really important for us to know how much iron we've got in a certain amount of iron oxide. So this problem on here has got 3 different steps. The first step is that we need to calculate what the relative formula mass is of iron oxide. So if we look at the periodic table, we find that iron has got an AR of 56 and oxygen has got an AR of 16. So we need to do 56 plus 56 for the 2 iron plus the 16 3 times for those 3 oxygen on there. And when we add all of that up together, we get a value of 160. The second thing that we need to do is we need to work out the percentage by mass of iron in iron oxide. And so the mass of iron is 56 plus 56 because we've got 2 iron present in there. And so that gives us our 112 on the top, but I'm just going to put it as 2 lots of 56 just so we can really see that there are 2 iron in iron oxide. And then on the bottom, remember, goes the MR value, so that's 160 that we've just calculated, and then we need to express that percentage by putting the multiplied by 100 at the end on there, and that gives us 70% iron. So iron oxide is 70% iron. Now that we know that, we are basically asking ourselves, if iron oxide is 70% iron, what is 70% of 200 grams? That's the final part of this problem. And so when you're working with percentages, you can write percentages as fractions. So 70% you would write as 70 over 100 on there. So that's 70% as a fraction. And so 70% of anything is 70 divided by 100 multiplied by whatever that thing is that you're trying to find 70% of. So we're trying to find 70% of 200 grams. And so 70 over 100 times by 200 is 140 grams. Now a similar question, but with a little bit of extra complexity built in as well. So we've got a fertiliser, and we've been told that the fertiliser is 37% nitrogen, and our task is to calculate what the mass of nitrogen is in grams, that's important, in 5 kilograms of this fertiliser. So we've got 2 different steps that we need to do, and actually we can do them in either order. I'm going to do the easy thing first. We have been told that we want our final answer to be in grams, but the first part of our problem is being given in kilograms. So I'm going to deal with that bit first. 5 kilograms, I'm going to turn that into grams. And the way that you do that is you multiply by 1,000. And so 5 kilograms equals 5,000 grams. So that was our first task. And then the second thing is, now we know that the fertiliser is 37% nitrogen, and we know now that we've got 5,000 grams of it, and so we need to find 37% of 5,000. And just like in the previous example, we can write the percentage as a fraction. 37% is 37 over 100. We need to times that by 5,000, and we get our final answer of 1,850 grams. Okay, so we're going to move on now to consider something which a lot of people, when they finish their chemistry course, actually say it was the most difficult part of the course, but actually it really needn't be, in my opinion. And so that is considering the mole and the Avogadro constant. Now, first up, before we go any further, we need to talk about this mole concept. Now, we're not talking about the animal or any other meaning of the word mole. We're talking about mole as a word for a number. Just like we know that a pair is 2, a dozen is 12, and a trio, we're talking about 3, those are all words for numbers. A mole is the same. A mole is a word for a number. So what's really important is that if you have 1 mole of a substance, you will have the same number of particles or atoms or molecules or ions or things in that substance as you would have in 1 mole of any other substance. Now, where it gets complicated, and I don't mean it's dead easy, but where it gets complicated is that number's a really, really big number. And that number is called the Avogadro constant, and it's named after an Italian scientist who did a lot of work in the 1850s about quantitative chemistry. He was called Lorenzo Romano Amadeo Carlo Avogadro, but we just call it the Avogadro constant because that's easier. But Avogadro's constant is 6.02 times by 10 to the 23 things per mole. And this is really important because atoms are really, really very small, so we need to talk about lots of them at once, and that's why Avogadro's constant is so big. Now, the power of Avogadro's constant is that we can talk about moles instead of atoms. So, for instance, if we had a mole of carbon atoms, we know that we will be talking about 6.02 times 10 to the 23 atoms of carbon. And if we talk about 1 mole of water, we will be talking about 6.02 times 10 to the 23 molecules of water. Where it gets even more powerful, a little bit more complicated, is that since water has got the formula H2O, which has got 1 atom of oxygen and 2 atoms of hydrogen, that's a total of 3 atoms per molecule. If we had 1 mole of water, it's got 6.02 times 10 to the 23 molecules of water in that quantity, but what it would have in terms of atoms is 3 lots of that number. So 3 multiplied by 6.02 times 10 to the 23 atoms in water. And so that would come out to be 1.806 times 10 to the 23 atoms. Although we'd probably round those to 1.81 because everything else was to 3 significant figures in there. The most profoundly useful thing about moles and working with them in terms of quantities is that the mass of 1 mole of a substance in grams is equal to the relative formula mass of that substance. And so what that means is if we've got carbon, which has got the numbers 12 and 6 that we know from earlier, if we have 1 mole of carbon, we know that its relative atomic mass is 12, and we know that 1 mole is the relative atomic mass or relative formula mass in grams, so it will be 12 grams, because what this means on here is effectively 12 grams per mole. Now, you don't need to use those units for GCSE level, but I actually think it's helpful, this grams per mole, to help you understand Avogadro's constant. And so if you've got 2 moles of carbon, it will have a mass of 24 grams. If you have half a mole of carbon, it will have a mass of 6 grams. And so you can apply that to atoms like we've just done there, but if we consider water, which we know earlier, water's MR is 18 grams per mole, then we can say that, okay, right, well, if I've got 3 moles of water, we know that there will be a mass of 3 lots of the relative formula mass, 18, which means 54 grams. And so we can say that in 54 grams of water, there will be 3 moles of water, and it will be 3 times by Avogadro's number worth of water molecules. And last of all, the power of moles is we can work out how many things there are present if we know the mass. And so if the question is how many moles of water do we have in, say, 90 grams, well, we know before 18 grams per mole is how heavy 1 mole of water is, and so the moles will be found by dividing our 90 by 18, and we get an answer of 5 moles on there. And the symbol for moles is just a slightly shortened version of the word mole. We just write mol, M-O-L. One of the hardest things you're going to be asked to do when you're working with moles is to calculate moles, mass, or MR. And what we've been doing on the previous page without actually talking about it is we've been using this relationship up here, moles equals mass divided by relative formula mass. And so obviously that's great. If you get asked to calculate the number of moles, you can just remember that one formula. But what you might need to be able to do is you might need to be able to rearrange it. And so to rearrange it using algebra, if we wanted to calculate mass, say, what we would have to do is we would have to multiply both sides of that equation by the relative formula mass, by the MR. And so what we'd have is moles on the left-hand side multiplied by MR is equal to mass on the right-hand side that was already divided by MR. We're now multiplying it by the MR as well. And what you'll know from maths is when you're multiplying something and then dividing by that same number, those two quantities can cancel each other out. And so overall, what we're left with is moles times by MR equals the mass. And so we've rearranged that into a form that you can use to calculate the mass of a particular substance. Now, what about if you weren't asked to calculate the mass, but you were asked to calculate the other one, and you were asked to calculate MR? So we need to get MR over on the left-hand side by itself. Now, the way that you do that is you need to divide both sides of the equation by moles. And so this time we've got moles times by MR divided by moles is equal to mass divided by moles. And that, when we cancel out moles divided by moles over here, they disappear. We're going to be left with MR is equal to mass divided by moles. So here are the three different forms of the equation that you might need to use. MR equals mass over moles, mass equals moles times by MR, or moles equals mass divided by MR. Now, what I know is that a lot of people don't like rearranging equations. You like using formula triangles. And I don't particularly like formula triangles. I prefer algebra, but we have to be open-minded. And so the formula triangle that you could use in this situation is mass, MR, and moles on here. And so if you are trying to work out what the mass is of a substance, you cover up the thing that you're trying to find out. And so mass is MR multiplied by moles. If you were trying to find out what the moles were, you would cover up the moles and you'd be left with mass over MR. Last of all then, I thought I'd leave you with a few problems to calculate for yourselves. So try these, freeze the screen, I'll pop the answers up in just a moment for you to check how you've gone on. Okay, hopefully now you've had a chance to have a go at those questions, so I shall reveal the answers. Okay, here are the answers popping up now for you to check off how you've got on. What I would say is the first ones are quite straightforward really. We get more complicated when we get down to the bottom. You have hopefully used the correct organisation for the MR equals mass over moles equation over here. Where these get most complicated is down here for C and for D, where we need to work out the number of moles that we've got present, but then recognise that there is more than one atom per mole, because I asked up here how many atoms there are in the following. So you've not just got to work out the number of moles, but then multiply that moles by Avogadro's number and then by the number of atoms in a particular molecule. So it was Avogadro's number times by 4 for the first one over here, and then for this second one where it was really complicated, we had to work out the number of moles. So 34 over 17 gives us 2 moles of ammonia, and so we have to do 2 times by Avogadro's number. That tells you how many molecules we've got, and then we need to multiply it by 4 because there are 4 atoms per molecule, which gives us this as our final answer down here, 4.82 times 10 to the 24. Okay then, right, thanks everybody for listening. I hope that was useful. More to come. Thanks very much. Bye-bye.